Good afternoon, ladies and gentlemen, and welcome to the very first webinar organized by the National Supercomputing Centre Singapore, or NSCC for short. Thank you for being here with us for today's online event on Future Cool Singapore, partnered with the Singapore-ETH Centre. My name is Alethea from NSCC, and for those of you who are not familiar with us, NSCC is a national research infrastructure funded by the National Research Foundation, NRF, of Singapore. NSCC is Singapore's first petascale computer facility that provides high-performance computing, or HPC, resources to all local research institutes, institutes of higher learning, government agencies, and companies in both the public and private sector. HPC resources are beneficial in a variety of ways and in a number of different sectors. It enables research of the highest computational complexity and data intensiveness in areas like advanced modeling and simulation, artificial intelligence, machine learning, as well as big data analytics for fields like genomics, biomolecular modeling, advanced manufacturing and design, digital twin technologies, weather forecasting, climate research, and quantum computing to be completed in shorter time spans. Supercomputers play a crucial role in sectors like fundamental research, biomedicine, precision medicine, healthcare, built environment, climate change and monitoring, offshore and marine, construction and design, automotive technologies, fintech, computational law, and robotics. If you are interested, do find out more about NSCC and HPC at www.nscc.sg. Advanced modeling and simulation research work is one of the main beneficiaries of supercomputing power. The ability to create a near real-world digital model or environment with potentially thousands of data sets and perimeters running simultaneously requires extremely high computational power and complexity, a job for which supercomputers are best suited for. Today's talk about Future Cool Singapore is a prime example of such an application. Prof. Gerhard Schmitt is a professor of information architecture at ETH Zurich, or the Swiss Federal Institute of Technology Zurich, and the founding director of the Singapore-ETH Centre, which was set up in 2010 by ETH Zurich and Singapore's National Research Foundation. As the centre's director, he leads a team working on research programs related to the Future Cities Laboratory, Future Resilient Systems, Cooling Singapore, and Natural Capital Singapore. He currently leads the Cooling Singapore project, which is aimed at mitigating the urban heat island effect. He will be joined for this talk by his colleague, Dr. Heiko Adyt, a computational scientist with expertise in modeling and simulation, as well as computer science with focus on software engineering of distributed systems. In Heiko's role as principal investigator and senior researcher of the Cooling Singapore 1.5 project, he conceptualized the idea of a digital urban climate twin, heavily influenced by his earlier work on symbiotic simulation. In the upcoming Cooling Singapore 2.0 project, he will lead the R&D of the digital urban climate twin to support urban planners and policymakers in their efforts to address the urban heat challenge. Before we get started with the talk, please do note that if you have any questions, do post them into the Q&A chat at the bottom of your screen so that the speakers can address and discuss this after the presentation. So without further ado, let me warmly welcome Prof. Gerhard Schmitt to get us started. Prof. Schmitt, please.
Thank you very much, Alethea. I hope you can hear me all. A warm welcome to you. I'm speaking to you from Switzerland and Heiko is in Singapore. Future Cool Singapore is the title of our webinar today. And Heiko, can you advance, please? First, a description of what Cooling Singapore is. It's for future urban climate design and management, very important climate design and management. It's an initiative that aims to have an integrated and holistic approach to address the urban heat challenge for Singapore and other cities around the world, because that is not unique to Singapore. Next. And here we have an example, the challenge that we are facing. You're looking top down from a bird's eye view on the CREATE buildings and the CREATE Tower and the CREATE Fingers, as they are called, of the National Research Foundation on the CREATE campus. And you see some features that we have to model when we want to model an entire city. You see the streets, that means the transportation but also what we call the passive anthropogenic parts, which is the asphalt and all these heat soaking materials. You see the trees in their very wild and irregular geometry. You see the cooling plant that you see in the center, this round object. You can also see some renewable energy being generated on the buildings itself with these photovoltaics, and you see lots of old and new buildings all mixed together. So this is the challenge, one of the challenges we have, and the biggest challenge, of course, which we'll see in the end, is not the technology, is not all these objects that are standing around, but it is the citizens, it's the people who use these facilities and who, through their behavior, change all the outcome of our simulations. Next is. I want to start with a big thank you to all the team. There's many people in the team now, the UHI work group, the partners, the scientific advisory committee, the steering committee, the NRF, and it is even a kind of homecoming to the NSCC. It was not called this way 10 years ago, but they were the first ones to give us access to connect us to the world from Singapore back to Switzerland. And I'm still thankful for that. I will never forget that. So this is another feature of a supercomputer center almost in every country. It doesn't do all the beautiful things only that Alethea mentioned in the opening, but it also connects people, connects ideas. Next is. Here you see a number of the people we are working with, not all of them, but these were the people in the project now, and this group will grow with Cooling Singapore 2.0 significantly. And you can see they're from Singapore, from all other places, all different cultures and nations in the world. Next is. You might ask, what does supercomputing and Cooling Singapore have to do with each other? Yes, of course, they have to do with each other. They are connected through the necessity to compute the different behaviors of buildings and trees and streets and cars and all of this. But there's more to that. Next one. There's also the question, maybe supercomputer and data centers are connected to the urban heat island effect. So at the same time, urban heat island can be a cause and a solution connected to the supercomputer centers. I remember when I first saw the, at this time, fastest computer in the world, supercomputer in the world, the K2 in Japan, and I saw the gigantic cooling plant right next to it almost a decade ago, then I knew these centers, these data centers, these supercomputer centers will have significant cooling loads for their surrounding. And this is, for example, why in Switzerland and also in other places, we try to locate supercomputers in places that can absorb a lot of heat in a natural way. Next. Why is heat so important these days? And with this one, I come to the first big part, which is the existential threat of global warming. You have heard a lot about global warming in every news it is, and now, of course, it's covered partially by the COVID discussion, but the global warming is going on. There are natural causes, there are artificial causes, there are human causes, and there are very active, fast causes, and there are longer investment causes. And we will look at them, some of them now in detail. Next is. There is a global risk of deadly heat. This is from a research done a couple of years ago, 3 years ago. And you can see here the whole map of the world. And you can see white parts, you can see yellow parts and more red parts. And the white parts mean there is no direct deadly risk of heat, rising heat in the world. But the yellow ones and the red ones, this is where the heat will come to a point that is really detrimental to health massively. And that means if you spend more than 2, 3, 4 hours outside during a day, it might actually lead to very serious damages of your health or even death. And unfortunately, when you look at this map, and if you know the demographics of the world, it is exactly in those places of the world where most people either are living already or will be living in the future, where this deadly heat will be very, very high. So you look at Asia, you look at India, you look at Africa. These are very, very big centers of present and future population development. And this is still independent from what we call the urban heat island effect, which we get to now. Next. And we can see here the different impacts that this will have. It will have impact on health because we can do less outdoor activities. We have reduced well-being. We have increasing healthcare expenses. It will be negative for the economy because productivity of everybody outside and possibly inside will go down. And it will make cities in those very hot areas less attractive as a destination for investment. And it will also reduce their livability. It will cause disruption through the increased occurrence of flash floods, for example, and falling trees, traffic disruption, and so on. Some of this we see in Singapore already and since a few years, but in other places in Asia, in the tropics particularly, this is much, much stronger than in Singapore. And it will have a lot of impact on the environment through the loss of natural capital. In Singapore, we still have beautiful natural capital, all the trees, the lakes, and so on, but it all is diminished by the rising temperatures that we have. Next. Why do cities matter? And why is there an urgency to act now? Why do we need supercomputers to help us simulate the effects so that we can do a mitigation, that we can change this course of development? Next is. We can see here that the urban heat challenge in the cities of the world is quite serious. The cities, they only cover about 3% of the world's surface, but they consume about 75% of the world's primary energy, and they emit more than 60% of the world's total greenhouse gases. So you can see a huge impact of the city. When you look at this map of the United States, in this case, you can imagine the cities, they are like needles of heat sticking out from the Earth's surface, and not only heat, connected to that is of course pollution and all other kinds of emissions. Next is. When we switch from United States there to the whole world, here is a map that was done last year, which is, I think, very impressive because it shows of every city in the world on which we have data, if and how big there is an urban heat island effect. The urban heat island effect, just to remind you, is the difference of temperature between the surrounding of a city and the city itself. And everything on this map, which is red or yellow, is warmer than the environment. However, you also see a few blue dots on this map, and these are places where actually the cities are cooler than the environment. And this can happen through an interaction between, let's say, a very dark surrounding area like rock and very white buildings and white streets, as we have it, for example, in Greek villages. So this map of the world shows the severity of the urban heat island effect all over the world. It's not a singular phenomenon in Singapore, but it occurs almost everywhere. And we have to do something against it because remember, this is about 60% of the world's emissions comes from these cities that you see here. Next is. We can also today put a number to the damage that this is doing to the world's economy. And the numbers are so staggering, they are quite amazing. This is a formula, this slide is a bit too small, but it could be up to $8 trillion in the next 20 years if the cities just keep going business as usual, and up to almost $4 trillion if we do very severe measures to bring down the global warming to the degree that is about 1.5 to 2 degrees. So there is a huge damage to the economy and other related issues in the world cities. And in order to avoid this, we have to do something. Next. In Singapore, now zooming in on Singapore, we can see that these are all pre-COVID numbers, of course, but we see that the temperature that you see on this chart here is rising in Singapore already since the 1900s, 1990s, very much more than 2000. And then we have two developments, possible developments. You see the red part and the blue part. So this is with and without measures. But in any case, temperature in Singapore will rise in the next decades up to 4.6 degrees in the worst case scenario that we have now until the end of the century. Next. And that will have negative consequences because diseases will have a big impact on the ecosystem. New kind of diseases will come up, that's new kind of animals will come to the island, not only in Singapore, but of course also to the cooler regions of the world. All the things that are in the tropics now are marching north and south and impact all of these other countries as well. The next. There's the impact on the energy and water and food nexus. You see on this map all the places on the earth that will be impacted negatively, if it's red or yellow, by rising heat, and not only food production, but water availability and energy availability. So you can see there's a lot of parts in the world where that will happen. Next. And in Singapore, of course, it will be also the problem of rising sea levels, which are already marching on. You can see the sea level is between 1.2 and 1.7 millimeter, increasing every year from 1975 to 2009. And this is accelerating now, of course, through the fast melting down of the glaciers in Greenland, for example, or in the Arctic region and the Antarctic, of course. And that will impact Singapore and all cities on the sea, in the sea at the same time. Next. It will also diminish the outdoor thermal comfort, and you can see that here in Singapore. Typically, people are very smart. They try to adapt. They use umbrellas and all of these devices for many years. But if the temperature goes up 1.4 to 4.6 degrees in the next decades, even that will not help, and you will not be able to spend time outside without being physically being damaged. Next. And this downpour of rain, which you have experienced, will occur more frequently. And this is also an important and dangerous thing to happen. And it happens in all tropical cities very frequently recently. Next. So what is Singapore's urban heat island? What is the cause for all of these effects that we saw now? We have a very brief rundown now, before then Heiko Adyt starts to give you the details about how to model this and how to make a digital twin of this whole city. Next. The urban heat island is described in many ways. It's not very simple to describe, but I give you a few reasons for that. First, we look at the Singapore land surface temperature that you can measure from satellites and that you can visualize, and how it developed over time. Next. You can see as different parts of Singapore, for example, the airport, and you see it in 1989, you see it in 2003, and you see it in 2018. And you see it's getting more and more red. That means the surface temperature and the temperature just on the ground is getting warmer and warmer. So that's one measurement. Next. You can see another part of Singapore, which is the Jurong area. Again, the same time steps, and you can see how it became warmer and warmer over time. Next, we can see here a little video, and that shows you the hotspots within Singapore. And this video is done with called Singapore Views that we developed at the Singapore-ETH Centre, which allows you to rapidly visualize very complex data. And of course, we're going to use that for all our simulations in Cooling Singapore 2.0. So you saw some hot, of course, the reservoir area, which is wonderful. And we can see, and this is more important here, Singapore is not alone. It's surrounded by already very hot areas in Malaysia or in Indonesia on the south. And all of this big area, you can see the quite warm it is compared to the hinterland, to the islands and to the sea around it. Next. So this is one part. Now we want to see the passive and active anthropogenic heat. What is that? This is the heat that humans, through their actions, either long-term actions or short-term actions, bring into the urban system. And here I give you some ideas of the anthropogenic heat that we can deal with, that we can dissipate and that we can mitigate. Passive first. Next. These are a few examples of passive actions that people have done and that we can also mitigate. We can do something against it. Next. And here we have climate responsive design guidelines that we can make to reduce the passive heat that we bring into the system. What does that mean? Now we see a lot of little slides coming up very quickly. Next. This is the work we did a few years ago, and next you see different parts of the city. We can work on urban geometry, and there you see all the breakdowns of urban geometry, all individual pieces we can work on vegetation, on water bodies, on shading of individual buildings and streets, on different materials and surfaces, on transport systems, and on energy systems. So the first, the urban geometry, the vegetation, the water bodies, the shading, the materials and surfaces, these are things that we decide, we plan, we invest on, these are long-term. Whereas the last two, transport and energy, of course, is a combination of passive and active. Now we come, next, to a short visualization of that. Here we can see how the different places in Singapore, the different densities in Singapore have an impact on the local heat impact and the measurable local heat impact. And you can see how we build interfaces with which we can study the effect of different building forms, building shapes, street widths, street orientations, orientation of the whole settlement in Singapore, and to see the effect on it on the local heat island effect. Next. Now a few examples for mostly active anthropogenic heat. Next. Here you can see the Singapore energy flow diagram. On the left-hand side, you can see all the energy coming into the island, for example, natural gas or crude oil being refined and so on. And on the right side, you can see how it is used in Singapore and for what. And there's just one circle at the bottom. This is the whole transportation sector. And at the top, you see very big sectors. This is industry and commercial buildings. And between industry and commercial buildings, of course, we have also all the supercomputer and data centers in Singapore. Next. Here we concentrate on the effect of this active part of the heat island effect in Singapore. And again, focusing on the transportation at the bottom right, we can see it has quite a big impact on Singapore. And therefore, it's worth to start, if we go out of taking heat out from Singapore, to start with this sector and then look at each other sector consequently. Next. When we add to this simple heat from input and output, also the heat that is generated, for example, in the power plants to generate electricity, which is used to run all the supercomputer centers, you see up there on the center top, this big pipe. It looks like a pipe, red pipe. This is all the heat set free from the power plants that then goes into the heat system of Singapore. Some of it is reused, but other parts are going in maybe to water, the atmosphere, and we have to also account for this in the overall picture. Next. And the heat, of course, is not done in one part. You can see how it's distributed. There's just one image where the heat from the transportation, where it occurs and when it occurs. So it's a spatio-temporal calculation of all this heat set free, this active anthropogenic heat set free in Singapore. Next. There's just one example how we can deal with that. That's an example of a traditional car where you have the amount of energy that is needed on the right side is 16.7 petajoule. And on the left side is what you have to put in as primary energy in terms of oil. And if you move to electric vehicles, the next slide, we can see it's still the same amount of energy needed to run the vehicle, but much less of energy, primary energy, even if we generate this electricity to run the vehicles by burning natural gas as it's done in Singapore. But we can go much further than that. Next. And this is the slide, the last slide, where we can see the temporal distribution of the urban heat island effect. If you run the slides, you can see how it is changing. The time is ticking in the top left corner. And you can see now the cars are all running in Singapore. They emit heat into the urban system. And then it slows down. Now 3 in the morning, 9, 10 o'clock, some breeze is coming from the sea. That doesn't mean it gets cold. It just gets as warm as the surrounding, maybe 30 degrees at this time. Then in the afternoon, heat is building up in these different parts of Singapore again 4 o'clock, 5 o'clock in the afternoon, all the cars are driving home. And then in the evening, the heat island effect is building up again in Singapore. And if you look where you are living, you can imagine it's also in your part where you have a very uncomfortable heat island effect overnight. Next. How can science design and inclusion help? Next. I want to go through this very quickly. In other parts of the world and in Singapore, science is acting very strongly to help to mitigate this effect. Here, for example, the Complexity Science Hub that was founded in Vienna together with Singapore and Switzerland is dealing with this in a scientific way, but also in Singapore and Switzerland we have next what we call a citizen design science, which is an approach between science, design and citizen science. Next. That shows us how we can integrate people into the heat mitigation, explore their preferences next, and find out where they will be willing to pay and to make things better than they are now. So they can rank these different options. They can put their money where they think it should be, where they would invest it themselves or where the government should invest it. And they give you quite a good indication where the money should be spent in the future and where in their neighborhoods these actions should be taken. So all you see here is always linked between physical environment and also people's opinions, people's experience at the same time. Next. And out of this then comes the willingness to pay for people in many case studies that we did. And we can see very clearly that people who are together or that have a family are willing to pay and invest much more into the improvement of the environment than people who are, let's say, single. Next. And this has gone into larger projects in Singapore, ideas for Tanjung Pagar, for example, together with the URA to identify parts of the city where new planning methods could be used and where completely emission-free parts of the city could come into place. Next. And here are some software examples we developed for that all have to be integrated in one huge urban city model. Next. And this is now the point where we have to put all of these things together to build this digital urban climate twin in order to simulate a future Singapore. And for this, I give the word to Dr. Heiko Adyt. Heiko, you are the man of this part. Please start.
Thank you, Gerhard. Okay, can you hear me now? Okay. Thank you, Gerhard, and welcome to my part of the talk. I will talk about the digital urban climate twin, and I will start first with the vision. So we have this idea of using what-if scenario analysis. The idea behind that is that we want to be able to give planners and decision makers the ability to experiment with simulations and say, okay, what happens if we do this? What happens if we do that? And the way how we do this is we build a digital twin, which is essentially trying to very closely imitate what's going on in the real world with a computational model. And that digital twin will be kept up to date using sensor data and insights that we gain from reality. And then this digital twin can be modified to reflect one scenario or the other. And based on that, we can then run the simulation for that specific scenario, whether it be district cooling, solar panels, electric vehicles, or anything else. And the idea is that this would then be able to provide useful information to planners and decision makers. Okay, so there is, of course, quite a number of things that we should talk about, and I'll give you an overview of some of these. The ambition is that user groups would include local agencies like the URA or the HDB, and some of the other agencies as well. It will also include academia, of course, like the Singapore-ETH Centre, local universities like the Singapore Management University, NUS, MIT Smart, TUM Create, and of course A-Star as well. At some point, we also hope to engage with industry. At this stage, it's very much still research, so we haven't done this yet. There will be a number of applications one of the bigger applications, videos you've already seen, is the decision support system, which we have been working on during the currently ongoing CS 1.5 project. And that is essentially what the user will see and use. Then there's, of course, the backend, the high performance simulation and computation environment. This is where all the models live and where all the high performance computing has to be done. And I'm talking a little bit more about the back-end stuff today. Okay, about the technical design for the digital urban climate twin. First, let's have a brief look at the principal components of this digital urban climate twin. Now, there is no such thing as a mother of all models. There is no one model that would incorporate all the different parts that we need in order to build a digital urban climate twin. Instead, we have a number of model components. So for instance, there could be an industry model, there could be a power plant model, there are models for traffic, mesoscale, microscale, and then of course, very importantly, we have urban climate models. Again, on the mesoscale and on the microscale. We generally distinguish between meso and microscale simulation workflows, but the idea is always the same, that we have different simulation models to look into the anthropogenic heat emissions, and then take the output of those and use them as input for the urban climate models. And then we can do UHI analysis, OTC, outer thermal comfort analysis, and also think about adaptation mitigation scenarios. In terms of technical design choices, there's some important decisions that we have to make or had to make. The first one is federation of models versus a monolithic model. I've already mentioned there is no such thing as a mother of all models, which would be a monolithic model that includes all these components. That's not feasible, partially because we have multiple highly specialized models. If you have an agent-based traffic simulation, that's a very different beast than an urban climate model. So you have different technologies as well. And also ultimately multiple owners. So there's different institutions, different organizations, and they have models which are highly specialized and work very well for a particular purpose. So trying to integrate this into one is just not going to work, which is why we're going for a federated model, a federated architecture. There's also the question about coupling. There is loose coupling versus tight coupling. So we have a loose coupling approach. What this basically means is that the output of one model can be used as the input for another model. Tight coupling is the case where you have two models which have to run alongside in a synchronized fashion while the simulation is running, which is technically a lot more challenging to do. But in the digital urban climate twin, we foresee mostly a one-way flow of data, so the loose coupling approach would work well. Although it does not preclude tight coupling. So there is actually some examples where we might need this tight coupling approach. And then there's of course also related to the federation architecture, a distributed deployment versus centralized deployment. I already said that it's not a single organization that owns and operates all the models. In fact, we want to be able to, for collaboration purposes, but also for operational purposes, be able to have models spread across different organizations. They can run their own model, and this model will then be part of this federation of models. And then you can run a distributed simulation across all these models. It also allows for more flexibility and more granular control. Because if, let's say, there are some things that an organization may not want to share, for instance, someone is running a power plant model, but they don't want to share too much of the insights inside the model. Well, all we need is an interface, and then we just take the output of that model and use it for the other parts of the digital urban climate twin without ever being able to access the model directly. Okay, so all this, with all these components, somehow they have to talk to each other. And that requires a sort of a middleware, which we call the simulation as a service infrastructure. And in the current project, Cooling Singapore 1.5, we have built a prototype for that. And let me just talk about it a bit. So this idea of simulation as a service is that think of executing simulations just like any other web service. You send a request and there's some number crunching going on, and at some point you get a response. And every model component should be realized as such a service. That's the general idea behind it. The choice of technology here is RESTful web services. Some of you may be familiar with it. It's a fairly commonplace today. REST services are used in so many web applications, and I can assure you that each and every one of you, knowingly or unknowingly, have already used so-called RESTful web services. They're very widely used. And the idea is, as I said, that each of these model components in the red boxes would be wrapped with such a RESTful service and provide standardized interfaces to facilitate interoperability between the components. That's the general idea. Design principles, of course, we could build a general purpose middleware. In case of tight coupling, there is actually an IEEE standard. It's called High Level Architecture, or HLA in short, which describes really in detail how tight coupling should work. And then there's, of course, middleware implementations for this standard. That is an example of a general purpose distributed simulation middleware. And we could do the same thing, of course, but we said, no, we don't want to do this. We don't want to have a generalized solution because it adds a lot of, well, it adds a lot of trouble and work. So we said we want to have a specialized solution. It should be specialized for the purpose of building a digital urban climate twin. And also, when given the choice between simplicity and complexity, the idea was to always take the simplicity rule, simply because we don't want to add features that aren't really needed. And avoid unnecessary functionality. The reason is simply that you have code bloat and you typically introduce unnecessarily problems. And then there's also a bit I guess, more on a conceptual level, the difference between simulation as a service and modeling and simulation as a service. There are examples out there where you have modeling and simulation as a service. Now, the thing about the digital urban climate twin is that we have a number of well-defined use cases and a set of validated models. And each use case uses the set of validated models, or a subset of that, in one way or in another. But there's generally no need for the end user to develop their own models. And in fact, that's not a good idea anyway, because they're not necessarily the experts for the modeling. So this whole infrastructure shouldn't necessarily offer modeling functionality to the end user. There's, of course, the ability for users to parameterize the scenarios and the use cases. That's fine within certain boundaries. But the end user shouldn't be the one that comes up with entirely new different models. Of course, modeled components can be added by the domain experts. So there's no limitation in that way. But we refer to it as simulation as a service because that's really where the emphasis lies, not so much on the modeling part. We have also implemented a number of prototypes. So for instance, we have implemented workflow automation as a demonstrator of workflow automation with multiple components. In this case, we've used the workflow that we had for calculating the UHI intensity or generating UHI maps, including that includes several steps. We've been using the WRF model, and there's a certain pre-processing that has to be done, which is done by this WPS component. And then the actual simulation is done by the WRF component. Now, we have to do this twice because we do this once for what you can see on the top, an urbanized scenario, and then for a hypothetical all green reference scenario. And then we calculate temperature difference, because the idea is that the urban heat island, per definition, is caused by the city and everything that comes with it. If you don't have a city, you don't have an urban heat island effect, per definition. Measuring, of course, you can also use measured values to calculate the UHI. But in this particular example, we've just chosen a model-based approach to calculate a reference temperature map, if you like. So that worked well. We've also had a setup with deployment of the various components. In this case, we used internal computing cluster at SEC with a rather modest 72 CPUs and a bit short of 200 gigabytes of RAM, whereas the pre-processing was done somewhere in the cloud, on a Google Cloud instance. And then there is also a so-called simulation as a service inspector, which allows me basically to look into this thing while it's running, and that was running on my local laptop. So again, this is already an example how this works in a federated manner, where not everything is running on a simple machine or a single cluster, but across multiple organizational domains, but also on multiple machines. We had a second demonstrator which demonstrated the interoperability with the front end, with the decision support system. There's some images there. I won't go into the detail, but basically we had a number of scenarios that looked into mitigation scenarios, taking certain actions like, okay, what happens if we have a urban morphology whereby we have a building typology that uses a podium on the ground versus an elevated podium, and just see what the difference would be. And there's of course the graphical user interface that allows users to explore these scenarios. Again, there was a certain deployment, this time slightly easier because this was only this one component involved, which was actually not so compute intensive. But the idea here was to show that we can also basically link this backend with all these components and the simulation as a service stuff together with this front end application. Okay. So the prototype is this what we built in the current project. And of course, there is a follow-up project. In fact, Cooling Singapore 2.0 officially started 2 days ago on the 1st of September. And the focus of this project will be really building an operational digital urban climate twin. And there's quite a bit of research that we need to do. I won't go into the details, but basically what the colors show you here is what we already have and what we don't have. So the red stuff, the red boxes is really what we don't have. And if you see green text like the traffic model microscale, this means that we have a microscale traffic model, but we haven't built that box around it yet. Basically, we haven't built the simulation as a service infrastructure component around it. And of course, even if I say we already have these models, it doesn't mean that these models are done. There's still quite a bit of validation work that needs to be done, and the models need to be improved. We are also planning to incorporate models from CCIS, the SingV model for the mesoscale, together with partners at NUS. And also we are planning to integrate the IEM model developed by A-Star IHPC for the microscale simulations. On the front end development, there will of course be the decision support system, which we will, based on the current system, we will already extend it. There will be quite a bit of focus on making sure that this data can be exported in a way that the agencies find useful for their own purposes. And these applications will be developed very closely with the end users in mind. So we will talk to the various agencies like the UAA and try to figure out what it exactly is that they need and how our tools can help them. More on the technical side, we will have these this inspector tool or inspector tools. They will help us to monitor what's going on in this digital urban climate twin, and they will be developed with the needs of the developers and technical users in mind. Deployment, there will be many different components. On the back end, of course, we have the SaaS infrastructure and the various model components. There will be high performance computing involved, and for that we will be working with the National Supercomputing Centre, but also others. There will be cloud computing environments, for instance, Google Cloud, but also others. We're not limited to Google. On the front end side, as I mentioned, there will be standalone applications like the decision support systems and possibly others. We will also look at web-based applications. So there's quite a number of developments going on there. Okay, so opportunities for high performance computing. Now, this whole idea of a digital urban climate twin is to be seen in the context of this idea of urban climate design and management. And what this exactly is, it basically refers to the ability to understand the climate science, modify and maintain the urban climate, temperature, humidity, and airflow on different urban scales, for instance, for the whole island or on a building scale, comprehend the social science of risk, and mitigate to achieve set targets and desired conditions accordingly. So as far as this is possible, I mean, we can't turn Singapore into Iceland, right? That doesn't work. But within the limits, within the boundaries of physics, what can be done? And the idea is that we provide planners and decision makers with a tool, and that is really the digital urban climate twin, that allows them to experiment with what-if scenarios. I mentioned already decisions. And this works in this loop that you can see on the right-hand side. So you have a scenario, you translate the scenario into a model, simulate it, analyze it, and modify it. And then you figure out that this isn't giving you what you're looking for. You modify the scenario, and then it basically goes in the loop until you have something that you're happy with. And that requires a lot of computational power. And this is where it gets us to HPCs. Of course, those of you who are familiar with high performance computing, you know there's limits to scalability. I mean, of course, if I need more speed, the assumption is, well, I just double the computational resources, for instance, I use more processors, and then the assumption could be that, well, my performance will also double. This would be linear speed up. Unfortunately, linear speed up is hardly achieved in reality. And the problem here is mostly that you have communication overhead. In any sort of parallel process, any parallel computation, you have communication overhead between the different processes. And this overhead is essentially causing you to experience sublinear speedup, which means even if I double the computational power, I get less than a double of speedup. And in fact, the more processing power I throw at a problem, in fact, it gets even worse, to the point where I don't get any more speedup. So the question here is, and this is something that we have to ask ourselves, of course, is, let's say you have 100 processors and 100 what-if scenarios. What should I do? Should I run 100 what-if scenarios, each with a single processor only? But it means I can run all my 100 scenarios concurrently. Or should I run 100 what-if scenarios, each with 100 processors, but this means I have to run them sequentially after each other. Because of what I already explained with the sublinear speedup is, the bad thing is that the scalability is limited. So the speedup that we can achieve for a single simulation run is limited. And if it gets even worse, the ugly part is that all this marginal increase in performance by just adding more and more processors is not only wasting computational resources, but also energy, which gets us back to the heat part that Professor Schmitt mentioned earlier, that computing centers also contribute to the urban heat island. But the good thing is, because we are not so much interested in super quickly simulating a single scenario, a single simulation run, we actually have to simulate lots of scenarios. So we actually have the good thing is that we can actually then have a better trade-off. But we say, well, we don't necessarily need the simulations to run all very fast. What we need to do is get our scenarios, all of them, done as quickly as possible. So we would actually probably use something more that's closer to option A. We will use less processors per scenario, but we can run many scenarios concurrently. That would actually make more efficient use of the computational resources. So opportunities for HPCs, generally in science, and these are just some examples, and it depends, of course, on your use case, but generally you have models requiring a lot of resources, and generally the researchers work on it, the simulation experiments, and they work directly with the HPC. They tend to be one-off experiments, so you may run some test scenarios, but then you run the experiment that you want to have, you collect the data and you do the post-processing, but you probably won't rerun the same experiments. For the urban climate design and management, actually, what we have is the HPC has to be somehow seamlessly integrated into this whole operation of the duct, because the end users, they don't want to be bothered with the technicalities of the HPC. And instead of having one-off experiments, we'll probably have to recurring and on-demand simulations. And I think this gets us to the opportunities. The ambition for Cooling Singapore 2.0 is, of course, to build this operational duct. And here we aim at technology readiness level 6. And the goal is not to deliver a perfect solution. We know this can't be done, but we want to have a solution that is intuitive and useful for the end users, the planners, the decision makers. So we plan to work really closely with the NSCC and others to ensure that the HPC resources can be tapped on in a seamless way. And this may not be necessarily the way how NSCC operates today, but this is why we need to talk about it, because I think in the future there will be much more such applications where HPC has to be seamlessly integrated into ongoing business processes. So one of the first steps that we should talk about is also how we can deploy these SaaS infrastructure and the components in the HPC environment. Thank you very much. At this point, I would like to pass back to Gerhard Schmitt to tell you more about Cooling Singapore 2.0. Thank you.
Thank you very much, Heiko. We are a bit short of time, so we rush through it very quickly. Maybe you advance to the conclusions, because we can go there quickly. Thank you. Here, this one is important. Sorry, what are other cities and countries doing? And it's not only in Singapore where this research is going on, many other places in the world, but very, very concrete. For example, in Zurich, next slide, where we have over the years already worked with the scientists in Zurich and planning for the future a Cooling Zurich project. Next, and you can see some of the visualizations you saw before have already been done in Zurich, but with other programs and with other simulation methods. As a matter of fact, in 2 hours, I'm meeting with the director of the Swiss Supercomputers Centre in Lugano to talk exactly about this and how we can possibly connect the two projects through computation and supercomputer computation. Next. The European Union is doing a lot on these on this level. And next, very concretely, a new program, Horizon 2020 next, in Horizon program, that 100 cities in Europe will be selected to become climate neutral. Of course, this is connected to huge investment in computation and simulation, how to do that. And so this is starting now. It's a brand new program. Next. Where do we want to be in 2050? I think we have always to think about this. What are the goals? What are the real goals for which we want to use supercomputing and all these other mitigation and adaptation strategies? And just to run through them quickly again. Next, for Singapore, of course, we want to have high outdoor thermal comfort. We want clean air. We want clean industry. And next, there's more points. We want less noise, we want renewable energy, and we want circular economy. So when you remember the first slide, when you saw the crate building from the top, many of these things are already starting to be implemented there. But there's much more to do. Next. Because every city has its own DNA, and not only every city at the top, you see Singapore, at the bottom you see Zurich, but even part of Singapore has its own DNA. So it has to be very, very customized for each part of Singapore, for each other city. We want to export all this knowledge to other places so that this knowledge can be used around Singapore as well and exported. Next. We want to work with the population because this is the big influence, how people behave, the behavioral aspects, the social sciences have to be in this project, has to be quantified in order to make a more holistic model. Next. So we are convinced that Singapore can reduce its urban heat island effect. It will significantly increase the outdoor thermal comfort and the air quality. It will reduce the noise and the CO2 emissions, and it will contribute to reducing climate change while improving urban health. And we are convinced that supercomputing will play a major role in this process. Next, and thank you.
Okay, thank you, Prof. Schmitt and Heiko, for the great and insightful sharing. So we've actually got a few ongoing questions from the attendees. Thank you everyone for submitting your questions. So now let's take the time for both Prof. Schmitt and Heiko to answer some of the questions live. So one of the questions that we have from Flo, have any measures which are based on those simulations already been implemented, or are we still in the research/setup stage?
Yes, maybe an answer to that. In the process of verification and of simulation, we have selected several places in Singapore as case studies. And so in these case studies, when we go there and we can plant the measurement instruments and the sensors and so on, we can make a direct comparison between the simulation and what is there in reality. So this is been done, it is successful, and from that we can also calibrate our models. Of course, it cannot build a city quickly and then validate it and implement it, but all the places, at least in Europe where we have done that before, the predictions and the simulation come very close to what we actually build if we can anticipate the behavior of the people using them. A city is not a machine, a city is not an automated machine that you can completely control. You always have to consider the human behavior in it, and to calculate and measure this and predict this is the most important part.
Okay, thanks for that, Prof. Another question from Aviva. Since you are running the simulations for the entire Singapore, you are dealing with a huge computational domain. Could you give an idea of typical computational times or resources to run? Example, a CFD simulation for SG, or are the simulations being run for different districts separately?
Yeah, Heiko, go ahead.
Yes. So it really depends. So we do several things, right? We simulate the whole of Singapore on a meso scale. It's basically a 300-meter resolution grid with MORPH, and it depends. So the kind of simulation what I mentioned earlier is about 72 CPUs, so that's a fairly modest amount, I would say, and I achieve roughly real time. So it's a tick faster than real time. In other words, it takes me about 1 hour to simulate 1 hour. My colleagues run different setups with different configurations, and those simulations can also run for several weeks because they're investigating longer time periods. On the district scale, another thing I should say, we don't run a CFD simulation for the whole island. So what we do is on the micro scale, there we run CFD simulations. I can't give you the exact numbers for that, except that they are more computational intensive. That's a question that some of my colleagues could answer better. But basically, to cut the long story short, is really, it depends on the scenarios that we have. It also depends on the environments that we have. So we have different access to different clusters. For instance, the in-house SEC cluster, which has a different hardware setup than what the colleagues at MIT have. I've also been using Google Cloud, which is a very different animal as well. So it really depends.
Okay.
Yes, there's also this question on the outputs are mainly meant for policymakers. Are they plans to release some data sets to the public? I found this a very interesting question. There was one before, which I answered. In the short term, and as a first output, of course, these will be many use for the planning agencies in Singapore and the policymakers in Singapore, because they need that for medium and long-term decisions. But in the long term, I can imagine very well that the outputs will be almost real time. This is another question that you had. And if they're almost real time, they can be very useful for the general public to predict, for example, where in Singapore at a certain time they should go jogging and where not. This is already done today very roughly, but you can make these simulations much more fine. They can also help people in real time decide where to rent a building or not. So many of these things should become available to the public, similar to how the weather forecast is done today. And this is a very strong similarity. And there was also the question, how much heat that will input into the urban system. This is a very interesting question. We are computing. For this, of course, we need the data from the data centers and from the supercomputer centers. And then we can calculate the heat input into the urban system, where it is and when it is. And for that, we can use the experience we already have, let's say, of district cooling centers in Singapore and how that dissipates in the city or not. In general, we will see by now in the world, it's about between 1% and 5% of the energy being used, the electricity being used for data center. That will be the case in Singapore as well, even more maybe. And of course, the data centers become much more efficient. The supercomputers much more efficient, so less heat is released per computation. But again, just like in buildings and in cities, so many people are in cities, and people, they want more and more space. So although per square meter the space gets much more efficient, overall the energy demand is still rising, and I can see similar development in supercomputing. But there has to be a point where it goes down, and if you use renewable energy to run these centers, that will be one big break for urban heat. More questions? You want to?
I think we have
pick one.
A few more questions. There's two questions from Ramonsa. First question, what kind of surrogate models do you use in the digital twin? Are they data/machine learning models or only physics-based? That's the first question. For the second question, tight or loose coupling refers to model execution or also involves model design?
Yeah,
Yes,
I can
Heiko.
answer that. So we actually don't use surrogate models yet, but this is something that we have on our research agenda. That's something that we would like to look into. The idea would be, generally speaking, that we have these very compute and time-intensive climate models. The idea was, well, can we replace basically this box with another box, a so-called surrogate model that would use machine learning methods, for instance, deep learning, as an example, that would be able to give us a quick answer much faster than running a full-blown climate model. The idea here would be that the use case could look like this. If you have 100 scenarios, you could use the surrogate model to quickly evaluate all of them and then select, let's say, 10 out of those 100 scenarios which are most promising, and only those you simulate with the full-blown climate models. So it's a bit, the idea is to use these surrogate models as a way of or shortlisting interesting scenarios while using less computational power. But just to be clear, we haven't actually built those yet. The question of tight and loose coupling, it refers to the model execution. So if you have two models that affect each other, so for instance, as an example, you have an air conditioning model and well, the climate model. Now, if it's hot outside, then the air condition has to work harder and in order to reduce the temperature indoors to a certain set temperature. Now, if it needs to work harder, it also means it ejects more waste heat. So there's a bit of a circular relationship between these two models. There's different ways of doing it, but one way would be that you would tightly couple these models. So they would basically run alongside. Currently, actually, in the WRF model, it's all inside the WRF model, but in the future, this may be different. So yes, this refers to the case of model execution.
Okay, I think we have time for probably 1 to 2 more questions. So another question that we have is from Xu Sheng. Currently, the ask and criteria for the green buildings is well developed, but the impact of these green buildings on the surroundings, spaces between buildings, public spaces, and other buildings is still very limited. Could this research help, and how to help with this, both for the people using the city and the better urban governance?
Yes, this is a great question. And if you remember the Sankey diagram that I showed in the middle of the presentation, you can see that actually the buildings in Singapore are not responsible for most of the active anthropogenic heat, but for quite a bit of the passive anthropogenic heat through their mass and their position and their density. But we know that green buildings can help to remedy this a little bit. And green doesn't mean painted green. It means really that they have either plants on the outside that can absorb and reflect some of the heat and make people feel cooler. This is a very important psychological effect, but also that their overall energy use is much lowered. But it's interesting, even if you look at all the HDBs in Singapore together, their anthropogenic active heat output into the system is less than 6% of the entire energy going or is being used in Singapore. So it's very limited. But dense buildings can do much more by changing their facades in the long run from absorbing the heat from the sun every day to giving them a new skin that can actually produce energy and at the same time protects the mass of the buildings from sun coming into it. So this is something that's done widely more and more here in Europe, that buildings get a second skin and that blocks the sun from getting into the building structure, into the concrete, heating it up and leading to the nighttime heat island effect. And at the same time, during the day when it's hottest, the electricity produced with the skin can help to air condition and cool down the buildings. So that way we can do a lot, even in very dense city like Singapore, to break this peak of sun absorption, heat release in the evening, and at the same time cooling demands during the day when the sun is just burning down on the building. It's a very delicate balance that we have to find, but it is possible. And again, for this, we need really supercomputers to compute that in the micro scale of individual buildings.
Okay, great. Thank you, Prof. Schmitt and Heiko, for such an insightful sharing. I think that's all the time that we have for today. Thank you to everyone for joining us for our first NSCC webinar series. The recording of this session will also be uploaded on NSCC's YouTube channel, so do head there for a review of today's event. We'll also be dropping all attendees a follow-up email so that you'll be able to look for the recording of this event. So do also join us for our next webinar on urban flow modeling and solar forecasting using HPC by Dr. Harish Gopalan from A*STAR's Institute of High Performance Computing. Thank you once again to our speakers, Prof. Schmitt and Heiko from Cooling Singapore. And thank you everyone for your time. See you at our next online event. Bye.
Thank you.